So in this one, we're given this VI curve, and then we're asked to draw a time versus voltage and time versus current curve when voltage moved from negative 40 millivolt to 0 millivolt. And what we see is that there's two curves. One is instantaneous and another is steady state. So what that means is that when we move from one voltage to another, it's at the moment, at the instant of such change, it will follow the instantaneous curve. However, eventually it's going to follow the steady state curve. So what if we were to draw this time versus voltage and time, so that's the top, and then time versus current curve. So we see that at time 0 and at the voltage of negative 40 millivolt, the current is also 0. So that's what we got going on here on the top and bottom. They're all 0, and at time 0 voltage is negative 40 and the current is 0. And then we're going to a voltage of 0 millivolt, correct? Right? And in such case, when the V is equal to 0, we have the instantaneous, the solid line reaches the current of 3. So negative 40 millivolt instantaneously changing from negative 40 to a 0 millivolt, and then instantaneously we reach a 3 nanoamp per square centimeter. So it's going to go all the way up to 3 instantaneously, right? But eventually it's going to reach steady state value, which is dotted line, and that is 4. So we can see some exponential curve like going to like that, 40 to 4. And the important part is that what is the time constant, right? So voltage is just gonna it's gonna stay for 0 millivolt but in this case, a part where it reaches 63%, so it's gonna be, the magnitude is gonna be 3.63, because that is the magnitude of the steady state change, not the entire thing. And the time that it reaches the 3.63 is the time constant. And in this problem, if we go back to the previous slide, it was given that this is the time-dependent current flow follows a first-order kinetics with a time constant of 0.1 second. So in this case, this would be 0.1 second. On the second problem is asking, so the only thing that's changed is the voltage going from negative 40 to negative 80 millivolt. So in that case, the answer is already shown in here, but so we can do the same thing for voltage. Time versus voltage curve is going to go from negative 40 to negative 80 instantly, and then it's just going to stay there. For current, we see there's two curves again, instantaneous and steady state. And instantaneously, you will follow the instantaneous, the solid curve, which goes to negative 80. So it's around, I guess like 0.05? No, 0.5. So let's say instantaneously it's going to reach negative 0.5. But afterward, it's going to follow the steady state, which was the dotted curve line here, and it's like around negative 1. So once the instantaneous change has occurred, it's going to follow this exponential curve. And the point where the 0.63% has happened, so in that case, it will be 0.5 times 63, 63%. So that's like 30, let's just say 30% for the sake of easiness. And 30% times 0.5, so 0.8-ish. In terms of amplitude, so nanoamp. And that's the time constant again, and which is the 0.1 second. Third question is asking, what if the voltage go from negative 80 to negative 100 millivolt? So voltage, again, it's pretty easy. So it's sitting at negative 80 at time 0, and then it's going to change to negative 100 millivolt, and then just going to stay that way. For current, so it's staying at negative 1, a nanoamp per a nanometer square. As you can see, because of the steady state, that's where we started off of. And then it's going to move to negative 100, and we may say, oh, shouldn't it follow the instantaneous change? But it's already at the same steady state value as the negative 100 millivolt, which is the energetically most stable position. So it's just going to stay at the same negative 1 steady state value. So actually the change is none in the current.